All right, friends. I hope this is the last time I'm working through this problem. I have discovered way too many mistakes with the typing of this question into the Calculus BC Common Assessment, and I'm gonna try working through this so that you can see the question as it was written by the College Board. So here we go. We're going to consider the differential equation dy dx equals -1 plus y squared over x. And we need to show that d squared y dx squared, your second derivative, is equal to 2y cubed minus y squared minus 2xy over x squared. Well, I would hope that everybody watching the video knows that when I say d squared y dx squared, what I mean is the second derivative. And the way that we're going to find the second derivative is you find the derivative with respect to x of your first derivative. And I really want to emphasize this derivative with respect to x. The derivative of -1 is 0 because -1 is a constant. Plus, I need to take the derivative of this quotient. Using the quotient rule, you may know it as low d high minus high d low all over low low. It's the denominator times the derivative of the numerator. Because we're taking the derivative with respect to x, the derivative of y squared is 2y times dy dx minus y squared times the derivative of x all over x squared. That's good, that's great, that's your derivative. But that's not in this form, so let's clean this up. 2xy times dy dx minus y squared over x squared. That's still not what I'm looking for. The issue is I have the dy dx expression in there and I don't want it. But I was told in the beginning that dy dx is equal to -1 plus y squared over x. So let me rewrite this as 2xy times -1 plus y squared over x minus y squared all over x squared. If you distribute the 2xy through, 2xy times -1 is -2xy. 2xy times y squared over x, the x's will cancel. You'll have 2y times y squared, which is 2y cubed, and then minus y squared all over x squared. And that is exactly what we were supposed to show. The College Board awarded 1 point for the quotient rule, and I'm assuming that's the quotient rule with the dy dx left in there, and then 1 point for being able to simplify and show that your second derivative has that exact form. So that is a total of 2 points there. Okay, let's keep going. Part B says, let y equal g of x be the particular solution to the differential equation dy dx equals -1 plus y squared over x, with initial condition g of 4 is equal to 2. Does g have a relative minimum, a relative maximum, or neither at x equals 4? Well, what do I know? I know that y equals g of x is a solution to the differential equation, but I don't actually know what the graph of y equals g of x looks like. Is there anything here that's going to be helpful? Well, what I know is this. If I plug dy dx, if I evaluate my derivative at the point 4 comma 2, I get -1 plus y squared over x. That's -1 plus 4 over 4, which is 0. What this tells me is that I have a horizontal tangent line. Now, that's good. That's not good enough. My graph y equals g of x has a horizontal tangent line at the point 4 comma 2, but that's not enough to determine relative max, relative min, or neither. A relative max with a horizontal tangent line looks like that. A relative minimum with a horizontal tangent line looks like that. But what if what I'm really dealing with is a saddle point in which case I'm neither a max nor a min. The way that you make a determination is you look at now the second derivative. So we're going to look at the value of the second derivative at 4 comma 2. And remember, they already gave that to us up here. And if I do that, I've got 2 times 2 cubed minus 2 squared minus 2 times 4 times 2 over 4 squared. Well, let's clean this up a little bit. 2 cubed is 8 times 2 is 16. 2 squared is 4. 2 times 4 times 2 is 16 over 16. If I simplify this further, you're going to get negative 4 over 16, which is negative. What I know is y equals g of x has a horizontal tangent line at 4 comma 2 and is the second derivative is negative and is concave down. If I have a horizontal tangent line and concave down, what this means is we have a relative max at the point 4 comma 2. What we just used is called the second derivative test. You know that you have a horizontal tangent line, you examine the concavity, and from that you can conclude that you have a relative max. College Board awarded 1 point for considering the value of the derivative at that point, and the second point for the answer with justification. So that was 2 points right there. Not too bad. Let's keep going. Okay, now in part C, let y equal h of x be the particular solution to the differential equation dy dx equals negative 1 plus y squared over x with initial condition h of 1 equals 2. They want me to write the second degree Taylor polynomial for h about x equals 1. Now wait a second. When we write Taylor polynomials, you need to know a couple of values, especially if it's going to be the second degree Taylor polynomial. What you need to know is you need to know the value of your original function at the point. Okay, we've got that. You need to know the value of the derivative, and you need to know the value of the second derivative. So we've got a little bit of work that we have to do here. So let's see, dy dx at 1 comma 2, I can plug it in here. We're going to get negative 1 plus 2 squared over 1. I think if you do that correctly, you get 3. We need the value of the second derivative at 1 comma 2, and we did that work earlier. In part A, we know that that is going to be 2 times your y value cubed minus the y value squared minus 2 times the x times the y all over the x value squared. If I simplify that, that looks like 16 minus 4 all over 1. Sorry about that. So you get 8. H of 1 is equal to 2. H prime of 1 is equal to 3. H double prime of 1 is equal to 8. When you write a Taylor polynomial, you need to know the center. H, the center is 1, and now your polynomial has the form 2 plus the value of the derivative over 1 factorial times x minus 1 plus the value of the second derivative over 2 factorial x minus 1, the whole thing squared. You can simplify that if you want to. Sorry if I didn't plan my space well here. 3 divided by 1 factorial is 3. 8 divided by 2 factorial is 4. So there's your degree 2 Taylor polynomial. 2 plus 3 times x minus 1 plus 4 times x minus 1 squared. There was absolutely no need to reduce it, and really it's kind of silly to go about doing that. They awarded 1 point for using the values of your first and second derivative, and then an additional 2 points for your Taylor polynomial, for a grand total of 3 points. All right, friends, here we go. This is the very last part of question number 6. It's an error analysis question, and I've already made a mistake. I needed to restart. Okay, part D. For the function h given in part C, it is known that the absolute value of h triple prime of x is less than or equal to 60 for all x in the interval 0.9 less than or equal to x less than or equal to 1.1. Let A represent the approximation of h of 1.1 found by using the second degree Taylor polynomial for h about x equals 1 from part C. Use the Lagrange error bound to show that A differs from h of 1.1 by at most 0.01. I've been teaching Calculus BC for a couple of years now, and still Lagrange error problems always make me stop and think for a little bit. So what's going on? We know that the absolute value of your third derivative is going to be less than or equal to 60 on this interval 0.9 less than or equal to x less than or equal to 1.1. I don't know what the third derivative is. I don't even know what the original function is, but I do know, because they told me, that the absolute value of the third derivative is less than or equal to 60 if I'm on this interval. A is the approximation to h of 1.1. And they want me to show, found by h is the approximation to h of 1.1 from using my degree 2 Taylor polynomial. Well, what Lagrange says is this. If I look at the difference between the true value, right? H of 1.1 is the true value of the function at 1.1. A is your estimate from the second derivative. What Lagrange says is that this has to be less than or equal to, basically, if you look at the third term in your Taylor polynomial, not third term, but your degree 3 term, it would be h triple prime of x divided by 3 factorial times the difference between the point that I'm approximating in my center cubed. If I look at the maximum value of that third derivative on the interval containing the center and the point that I'm estimating, so I want the maximum on this interval 1 to 1.1, that the error, that's this difference between the estimate and the true value, is always going to be less than or equal to the maximum over here. Well, let's see if we can puzzle this out. What is the maximum value of the third derivative on the interval containing the center and the point being estimated? Well, we know that the maximum value of the absolute value of the third derivative is 60, so this must be less than or equal to 60 divided by 3 factorial times 1.1 minus 1, so that's 0.1 cubed. Well, that's already pretty. What do we have here? We have 60, 3 factorial is 6. 0.1 is the same as 1/10 cubed. The 60 and the 6 I can reduce. Now I've got 10 times 1/10 cubed. 1/10 cubed is 1,000. I can reduce, and I get 1 over 100, or if I need to, I can express it as a decimal as 0.01. Lagrange says that the difference, just one more time, between the estimate that I get from my Taylor polynomial and the true value, that's the error, is less than or equal to the maximum value of the absolute value of the next derivative divided by 3 factorial times 1.1 minus 1 cubed. Basically, all of this is the degree 3 term in your Taylor polynomial. We were able to work it through and simplify and show that that error is less than 0.001. The College Board awarded 1 point for what they called the form of the Lagrange error bound, and then 1 point for the analysis. This is the analysis, for a grand total of 2 points. That's that. Congratulations. We're done.